welcome. As you lie in bed right now, just settling into the quiet of the night, I want you to consider the mattress beneath you.
Mm-hmm.
It feels solid, right? Dependable. Maybe it's just a collection of fabric, foam, and springs. But according to the deepest, most fundamental laws of physics, that bed is not just a resting place. It is a massive, tightly coiled reservoir of trapped, explosive energy.
It really is. And tonight, as you drift towards sleep, we are going to unpack the invisible architecture holding your room together and trace it all the way out to the most mysterious, silent structures in the cosmos.
Yeah, it is a gentle journey of the mind. We're going to drift through the very fabric of reality. You don't need to take notes, and you don't need to memorize any equations.
Right, absolutely not. Our goal is simply to let the grand, sweeping concepts of the universe wash over you, providing a deeply factual but, profoundly peaceful landscape for your thoughts to wander.
So, the mission of our deep dive tonight is to explore this invisible architecture. We're going to start at the dawn of modern physics, in the miraculous year of 1905, and we'll travel outward, gently drifting into the dark, silent hearts of black holes.
It's quite a journey.
It is. And to guide us, we have a really fascinating stack of sources. We will be softly unpacking the historical papers of Albert Einstein, analyzing astronomical data captured by the Event Horizon Telescope, and exploring studies on the thermodynamics of the cosmos.
Yeah, plus the very latest research on the curvature of spacetime. It is a beautiful, ambitious collection of human curiosity. All of these minds, across generations, attempting to understand the mechanics of the dark.
And as you settle in, let us remind you to check out the YouTube channel Decoding the Dark. If you enjoy drifting through the cosmos with us, please like, subscribe, or leave a reaction or so. It really helps us continue these nighttime voyages.
To understand the dark, we must first understand the light. And, of course, the space it travels through. I want you to close your eyes and imagine the universe.
Just a giant empty void, right?
Yeah. Well, that's what we're usually taught, right? To picture outer space as an empty, cold void, just a blank, static canvas where things happen to exist. But I invite you to reimagine it tonight. Picture the universe not as an emptiness, but as a gentle, rolling ocean.
A rolling ocean. That's a nice image.
It's a dynamic, vibrating fabric that responds to everything within it. It's a living geometry.
That living geometry is exactly what we are going to explore. But before we can visit the extreme, quiet depths of a black hole, we have to understand the fundamental rules of this cosmic ocean.
We do.
And to do that, we travel back to one specific miraculous year, 1905. The setting is Bern, Switzerland. Albert Einstein is just a young patent clerk.
He's not a distinguished professor. I mean, he doesn't even have access to a full university library.
Right. Yet, in the span of just a few months, he publishes 4 papers in the journal Annalen der Physik that will completely dismantle and rebuild our understanding of reality.
The scientific community calls it his annus mirabilis, his miraculous year. To fully appreciate what he did, you really have to understand the scientific climate of the early 1900s.
People thought physics was basically solved, didn't they?
Exactly. Many prominent physicists believed the great discoveries had already been made. Physics was viewed as nearly complete, save for a few lingering mysteries, a few small clouds on the horizon.
But Einstein looked directly at those clouds. One of his first accomplishments that year was proving, mathematically, that atoms actually exist.
Yeah.
Wait, I feel like we need to pause there. We take atoms as an absolute given today. It's taught in elementary school.
Yeah.
But in 1905, that was still a subject of debate.
It was a fierce debate. Leading scientists like Ernst Mach viewed atoms merely as useful theoretical fictions, just a mathematical convenience to explain chemical reactions.
Oh, wow.
Yeah, they argued that if you couldn't see an atom, you couldn't definitively claim it was a physical reality. So Einstein set out to prove them wrong by looking at something called Brownian motion.
Right, named after the botanist Robert Brown.
Exactly. Decades earlier, in 1827, Robert Brown had looked through a microscope at tiny particles of pollen suspended in water. He noticed that the pollen grains were constantly jittering, just dancing around in a completely random, erratic way.
Kind of vibrating in place.
Yeah. Initially, he thought the pollen might be alive, but he tested glass dust and soot, and they jittered too. And for nearly 80 years, no one could adequately explain why.
So how did a patent clerk in a dusty office solve it? I mean, how do you measure something you definitively cannot see?
By analyzing the echo of the invisible, Einstein applied statistical mechanics to the problem. He realized that the water wasn't a continuous, perfectly smooth fluid. It was made of discrete individual water molecules.
Mm-hmm.
These molecules were incredibly tiny, moving rapidly and constantly bumping into the much larger pollen grain from all sides. Because the collisions were random, at any given microsecond, slightly more molecules might strike the left side of the pollen than the right, pushing it slightly to the right.
It is such a beautiful visual for you to hold on to as you rest in your room right now. Imagine dust motes lazily drifting in a shaft of sunlight.
It's a perfect analogy.
You can't see the air molecules pushing them around, but you can see the macroscopic result of those invisible, gentle collisions.
And Einstein didn't just suggest this was happening. He provided the exact mathematical formula linking the temperature of the fluid, the size of the visible particle, and the microscopic movements.
So he actually calculated it.
He calculated the size of the invisible molecules based on the visible jitter. It was the undeniable mathematical proof that matter was granular, atoms were real.
But he didn't stop with matter. He immediately turned his attention to light. And this is where he challenged another massive assumption at the time. He tackled the photoelectric effect.
Yes, he did.
Up until this point, the universally accepted theory, which was proven by James Clerk Maxwell's elegant equations, was that light was a continuous wave spreading through space.
Right, a continuous wave. But there was a problem with that. When scientists shone light onto certain metal plates, the light would knock electrons out of the metal, creating a tiny electrical current. This is the photoelectric effect.
Okay.
If light were a continuous wave, shining a very bright, intense beam of low-frequency red light should eventually build up enough energy to knock an electron loose. But it didn't. No matter how bright the red light was, nothing happened.
Huh.
Yet even a very dim beam of high-frequency blue or ultraviolet light would knock electrons loose instantly. The wave theory simply could not explain this threshold.
So Einstein proposed a radical solution. He suggested that light isn't just a smooth, continuous wave. It is actually quantized.
Exactly.
It travels in discrete, finite packets of energy, little indivisible droplets of light that we now call photons.
And the energy of each packet is tied directly to its frequency. The equation is beautifully simple. E equals hf. Energy equals Planck's constant times the frequency.
So red light just doesn't have the punch.
Right. A packet of red light simply doesn't have enough energy to break an electron's bond, no matter how many red packets you fire at the metal. But a single packet of blue light has higher frequency, and therefore enough energy to knock an electron free immediately.
I have to admit, I've always struggled a bit with this. If light is made of discrete packets, why does a beam from a flashlight look completely smooth and continuous to our eyes?
Well, it's a matter of scale and, our biological limits. Think of a gentle rain falling on a quiet lake. If you zoom in, the rain is made of millions of distinct separate drops.
Right.
But if you look at the lake from a distance, the surface just looks continuously disturbed. Our eyes are simply not sensitive enough to see the individual photons raining down. They blend together into a continuous beam in our perception.
That makes perfect sense.
And what's remarkable is that this insight, that light is quantized, is what actually won Einstein the Nobel Prize in physics in 1921.
Not relativity, which is what almost everyone assumes. But of course, he published his special theory of relativity that very same miraculous year. And this is where the physics really start to stretch the imagination.
It really does.
Einstein stated that the speed of light, which is roughly 300,000 kilometers per second in a vacuum, is the absolute speed limit of the universe. And more importantly, it is constant for everyone, no matter how fast you are moving.
This is a profound departure from everyday intuition. I mean, if you are in a car driving 60 miles an hour and you throw a ball forward at 10 miles an hour, a person standing on the sidewalk sees the ball moving at 70 miles an hour.
Right. Velocities add up.
Exactly. Velocities add up. But light doesn't work that way. If you are flying in a spaceship at 99% the speed of light and you turn on a flashlight pointing forward, you would measure the beam moving away from you at the speed of light.
Okay.
And a person watching you fly by from a planet would also measure that exact same beam moving at the exact same speed of light. The speed of light simply refuses to change.
But if the speed of light cannot change, something else has to give. The math demands it. To keep the speed of light constant for all observers, space and time themselves must be flexible.
Precisely. Time literally stretches and slows down for you the faster you move. Space physically contracts in the direction of your motion.
It's mind-bending.
It is. Space and time are not a rigid stage where events happen.
Yeah.
They are deeply entangled into a single pliable fabric called spacetime.
And this realization culminated in his final paper of 1905, bringing us to the most famous equation in human history. E equals mc squared. Energy equals mass times the speed of light squared.
Yes.
Okay, let's unpack this because this ties back to the hook I mentioned at the very beginning. If mass and energy are the exact same thing, just in different forms, does that mean the very bed you are sleeping on right now, the blankets covering you, are actually just a massive reservoir of trapped resting energy?
What's fascinating here is that is exactly what it means. We usually think of mass as stuff and energy as action, but Einstein showed they are two sides of the same coin.
Just different states.
Right. The m in that equation, the mass of an object, is essentially a measure of its resting energy content. And because c squared, the speed of light multiplied by itself, is an astronomically large number, even a tiny amount of mass contains a staggering, almost incomprehensible amount of energy.
To put that in perspective for you, the energy resting quietly inside a simple glass of water sitting on your nightstand, if it could be fully unlocked and converted into pure energy, would be enough to power a major city for years.
It's incredible to think about.
It is frozen energy, resting peacefully in the form of matter.
And this concept sets the stage for everything that follows in our deep dive tonight. Because this resting energy, this mass that makes up planets, stars, and you, interacts intimately with the geometry of space.
Which brings us to a major blind spot. Special relativity in 1905 was brilliant, but it only mapped out how things move in flat space, traveling in straight lines at steady speeds.
Exact.
But the universe is not made of straight lines. We live in a cosmos of circles, orbits, and acceleration.
Yeah, the theory was special because it only applied to special cases, constant velocity. Einstein spent the next 10 grueling years trying to generalize his theory. He needed to explain how mass, all this frozen energy, actually interacts with the space-time fabric to create the phenomenon we call gravity.
And he did it with a beautifully simple thought experiment. It's known as the equivalence principle.
I want you to imagine you are waking up inside a closed elevator. There are no windows, no doors. If that elevator is resting on the surface of the Earth, you feel your weight pressing down against the floor.
Right.
Now imagine that same closed elevator is magically transported to the deepest, emptiest part of outer space, completely far from any planet's gravitational pull. But there is a rocket attached to the bottom of the elevator, accelerating it straight upward at 9.8 meters per second squared.
Which happens to be the exact acceleration of Earth's gravity.
Precisely. Einstein realized that inside that windowless box, there is absolutely no physical experiment you could perform, no pendulum you could swing, no laser you could shine, no scale you could stand on that would tell you whether you were resting on a massive planet or accelerating through empty space.
Because they feel perfectly identical.
Exactly. Therefore, Einstein argued, they are the same thing. Gravity and acceleration are fundamentally indistinguishable.
I'm going to gently push back here because I've always found this to be one of the trickiest concepts to visualize. I'm struggling to picture that. If an elevator is accelerating upward in space, the floor is actively moving toward me and pushing up into my feet. How is that the exact same as the Earth passively sitting there pulling me downward? Aren't those opposite physical actions?
It is a brilliant question, and it strikes at the heart of Einstein's genius. Newton taught us that gravity is a force pulling you down. But Einstein says, what if Newton was wrong?
Wrong about the pulling.
Right. What if the Earth is not pulling you down? What if the surface of the Earth is actually accelerating upward, pushing against your feet, keeping you from following your natural, unhindered path through space-time?
But the Earth isn't expanding like a balloon.
It isn't expanding in space, no. But the fabric of space-time itself is curved around the mass of the Earth. To maintain a fixed distance from the center of a curved space-time geometry requires constant acceleration. You are literally accelerating just by standing still on the ground.
And that leads us directly to general relativity, published in 1915. Gravity isn't a magical, invisible tether. It's not a force pulling things together across empty space like a giant magnet.
Oh, it's not.
Instead, mass and energy physically warp the four-dimensional fabric of space-time.
Let's step away from the common analogy of a heavy bowling ball sitting on a trampoline. It's visually appealing, but it's mathematically flawed because it relies on downward gravity to explain gravity.
Which is circular reasoning.
Exactly. Instead, visualize space-time as a massive block of clear jello. Now imagine embedding a heavy steel sphere right in the center of that 3D block. The jello doesn't just sink downward. The very grid lines of the clear jello are pinched and stretched, curving inward toward the sphere from all directions, top, bottom, and sides.
So if you were a tiny particle trying to move in a perfectly straight line through that block of jello, as you get near the steel sphere, Your straight path naturally curves inward toward it.
Exactly. The Earth doesn't orbit the sun because the sun is pulling it with an invisible rope. The Earth is simply trying to move in a straight line through the jello of spacetime, but the sun's massive weight has severely curved the local grid lines inward.
So the straight line naturally becomes a circle.
Yes, and matter tells spacetime how to curve, and curved spacetime tells matter how to move.
And it is not just the spatial dimensions that are curving inward. Time curves, too. This is the phenomenon of gravitational time dilation. A heavy mass literally slows down the passage of time.
It does.
The closer you are to a heavy, dense object, the slower your clock ticks compared to someone observing you from far away.
It is an established, measurable fact. The GPS satellites currently orbiting our planet have to constantly adjust their internal clocks because, being further away from the Earth's mass, their time moves slightly faster than the time on the surface.
Wait, really? If they didn't adjust, what would happen?
If they didn't account for Einstein's curved spacetime, our navigation systems would fail by miles within a single day.
Let's bring that incredible reality right into the room with you. But before we fall deeper into this gravitational well, into the truly extreme bends in space-time, a quick reminder to visit the YouTube channel Decoding the Dark. Hit like, subscribe, or leave a reaction or so to help us keep these cosmic deep dives coming.
It's greatly appreciated.
As you lie resting, realize that you are an active participant in this cosmic geometry. The frozen energy of your body is subtly, gently curving the block of clear jello around you. You are warping the localized space of your bed just as the Earth warps the space around it to hold the moon. Time is moving infinitesimally slower for your physical body than it is for the ceiling above you. It is a quiet, continuous dance of mass and geometry.
So we have established that a body curves the space-time around it. The heavier and denser the body, the sharper the inward pinch of those grid lines. But what happens if an object is so impossibly heavy and packed into such an impossibly small volume that it creates a curvature with no bottom?
The bottomless dip. This is where we leave the solar system behind and witness the birth of a black hole. It begins with the spectacular, violent death of a giant.
Throughout the universe, there are massive stars. Stars 10, 20, 50 times the size of our own sun. For millions of years, they live in a state of delicate, beautiful equilibrium.
Like a balancing act.
Exactly. Deep in their cores, nuclear fusion is occurring, smashing lighter atoms together to create heavier ones. This fusion releases an outward pressure, a tremendous explosion of radiation that perfectly balances the relentless inward crush of the star's own immense gravity.
It's a million-year-long tug of war. But eventually, the star runs out of fuel. It fuses lighter elements into heavier ones. Hydrogen to helium, carbon to oxygen, all the way down the periodic table until it creates an iron core.
And iron is the tipping point.
Right. Fusing iron doesn't release energy, it absorbs it. The outward pressure simply turns off.
And when the pressure turns off, gravity wins instantly. The outer layers of the star collapse inward at a fraction of the speed of light, hit the dense iron core, and bounce off in a spectacular explosion known as a supernova.
So bright it can outshine entire galaxies.
Yes, but we are interested in what is left behind in the silent dark, the core.
The remaining core continues to collapse. It falls in on itself under its own staggering weight. If that core is massive enough, surpassing a specific mathematical threshold, no physical force in the universe can stop the collapse.
None at all.
The atoms are crushed. The protons and electrons are squeezed together into neutrons, and even those are crushed. The matter becomes so dense that the curvature of spacetime pinches completely shut.
It creates a gravitational well so steep, a localized region of spacetime so profoundly warped, that the escape velocity required to climb out of it exceeds 300,000 kilometers per second. It exceeds the absolute speed limit of the universe.
And since nothing can travel faster than the speed of light, absolutely nothing can escape. Not matter, not radiation, not a single photon of light.
It creates a boundary in space, a spherical veil of no return, which physicists call the event horizon.
It's such a beautifully poetic name, the horizon of events.
It really is. Past this invisible line, no event can ever be communicated to the outside universe. It is severed from our reality. And what's truly wild is how small these horizons actually are compared to the cosmic giants that created them.
It is a profound concentration of mass. For a mass equivalent to our entire sun, if it could be compressed into a black hole, the event horizon would only be about 3 kilometers across. You could casually walk across it in less than an hour.
That's tiny.
And if you were to somehow compress the entire mass of the Earth into a black hole, its event horizon would be the size of a 9-millimeter marble. A tiny dark sphere holding the weight of an entire world, bending light itself around its edges.
It's almost hard to picture.
Here's where it gets really interesting. Let's imagine watching something falling toward that dark sphere. Because of gravitational time dilation, that bending and slowing of time we mentioned earlier, the closer an object gets to the event horizon, the slower its local time passes relative to us, the observers safely far away.
Yes. If you were sitting on a distant space station watching a glowing robotic probe fall toward the event horizon, you would witness a profound illusion. You would never actually see it cross the threshold.
Never.
Never. To you, the distant observer, the probe's descent would appear to slow down exponentially, becoming more and more sluggish. The photons of light it emits would have to fight so hard to climb out of that steep gravitational well that they would be stretched out.
So the light shifts.
Right. The light would shift from white to red, then stretch further into infrared, then into faint radio waves, becoming dimmer and dimmer. Eventually, it would just fade away into the black, appearing to be frozen in time, hovering just millimeters above the horizon for all of eternity.
But what about the probe itself? For the infalling observer riding along, what do they experience? Do they feel themselves freezing in time?
Not at all. For the infalling probe, their local time feels completely normal. They wouldn't feel themselves slowing down or stopping. They would just smoothly, quietly drift across the event horizon, falling down into the dark.
Wow.
But if they were to look back out at the universe they are leaving behind, the light from the outside world falling in after them would be tremendously accelerated. They might see the stars racing through their life cycles, potentially watching the entire future of the cosmos flash by in the mere moments before they reach the center.
If we connect this to the bigger picture, what actually happens inside that boundary? Once you cross the event horizon, what does reality look like? I've read that space and time literally swap roles, but honestly, that sounds like pure science fiction. How can a physical dimension and a temporal dimension just trade places?
It does sound like magic, but it emerges directly from the strict mathematics of Einstein's field equations, specifically something called the Schwarzschild metric. Outside a black hole, you have freedom of movement in space. You can move left, right, up, down, forward, and back.
Right.
But time is unidirectional. It drags you relentlessly forward into the future. You cannot move backward in time, nor can you stand still.
Right. Time marches on.
But inside the event horizon, the extreme curvature of the space-time jello becomes so severe that the radial direction, the spatial direction pointing toward the singularity at the center, takes on the mathematical properties of time. It becomes unidirectional.
So space acts like time.
Inside a black hole, moving toward the center is no longer a physical journey through space. It becomes your inevitable future.
So just as I cannot stop myself from moving toward tomorrow, I cannot stop myself from moving toward the singularity.
Exactly. Even if you fired rockets with infinite energy pointing away from the center, it wouldn't matter. All possible paths, all light cones inside the event horizon point inward. The singularity is not a place you visit. It is an event in your future. It's a one-way street in the most absolute, terrifyingly beautiful sense.
It is the ultimate shadow. It's called a black hole because no light escapes it. Yet paradoxically, the areas immediately surrounding black holes are not dark at all. They are some of the brightest, most violent, and most luminous objects in the entire universe.
Yes, the glowing dark. This is due to a phenomenon known as accretion. A black hole sitting alone in empty space is completely invisible. But black holes are often found in crowded galactic neighborhoods, surrounded by thick clouds of interstellar gas or orbiting companion stars.
And the gravity pulls all that in.
The immense gravity of the black hole acts like a cosmic vacuum, pulling that surrounding matter inward.
But the matter rarely falls straight down, does it?
Very rarely. Because everything in space is moving and spinning, the matter has what physicists call angular momentum. As it falls toward the tiny event horizon, the conservation of angular momentum causes the infalling gas to swirl around the black hole, spinning faster and faster as it gets closer.
So it flattens out.
Right. The opposing up and down motions of the chaotic gas clouds cancel each other out over time, flattening the swirling material into a disk. We call it an accretion disk.
Think of water spiraling down a drain. But in this case, the water is superheated plasma, and it is moving at significant fractions of the speed of light. As this gas orbits the black hole, the inner rings are much closer to the gravity well, so they must spin much faster than the outer rings to stay in orbit.
And that differential rotation, inner rings spinning faster than outer rings, creates an unimaginable amount of friction. The gas particles rub and crash against one another, violently shedding their orbital energy.
Heating up.
This friction heats the plasma to millions of degrees. It becomes so unfathomably hot that it emits massive amounts of thermal radiation, primarily high-energy X-rays.
The black hole itself is totally black, but it is surrounded by a blazing, glowing halo. And the dynamics of these disks are beautifully complex. The sheer radiation pressure pushing outward from all that intense heat is in a constant, delicate battle with the immense gravity pulling the material inward.
It's a chaotic environment.
And in many cases, this chaotic, swirling magnetic environment creates something even more spectacular: relativistic jets.
Indeed. The black hole doesn't just eat. It can be an incredibly messy eater. The plasma in the accretion disk is highly electrically charged, and as it violently swirls around, it generates colossal, twisted magnetic fields. A small fraction of the material swirling in the innermost edge of the disk gets caught in these tightly wound magnetic field lines.
Instead of falling past the event horizon, it gets caught in the magnetic tornado.
Exactly. It gets accelerated and blasted outward from the black hole's north and south poles. These jets of tightly focused plasma shoot out at nearly the speed of light, piercing through the host galaxy and extending for millions of light years into the quiet intergalactic void.
It is a mechanism of breathtaking power. Our sources describe it as the Blandford-Znajek process, a theoretical model where the very rotation of the black hole itself twists the magnetic fields, drawing energy from the spin of the dark sphere to launch matter into the cosmos.
It's quite dramatic.
These actively feeding supermassive black holes, with their glowing disks and piercing jets, are what astronomers call quasars, or active galactic nuclei. They're so blindingly bright they can be seen from the other side of the observable universe.
And what is truly marvelous is that in recent years, humanity has evolved from merely theorizing about these structures to actually photographing them.
The Event Horizon Telescope.
Yes, which is not a single telescope, but a global network of synchronized radio observatories acting as an Earth-sized lens. They managed to capture the very first images of the shadows of supermassive black holes.
It was a monumental achievement. We saw the glowing, lopsided orange ring of plasma surrounding M87, a titan sitting at the heart of a distant galaxy. And shortly after, we saw Sagittarius A, the quiet, supermassive black hole, sleeping at the very center of our own Milky Way galaxy.
Those images were a triumph of both general relativity and human engineering. The dark center in those images, the shadow cast by the event horizon against the glowing backdrop of the accretion disk, perfectly matched the geometric predictions Einstein's equations made a century earlier.
But not all black holes announce their presence with blinding light and blazing jets. Some are entirely silent. They drift through the dark without making a sound.
This is where we meet the dormant giants. Just recently, astronomers analyzing data from the European Space Agency's Gaia mission made a stunning discovery.
Gaia is a space observatory, tracking the precise positions and movements of billions of stars in our galaxy, right? Looking for tiny wobbles in their paths.
Exactly. They found an old star, just an ordinary aging star, doing a strange rhythmic dance. It was orbiting what appeared to be a completely empty patch of space.
But the space wasn't empty.
No, it wasn't. By carefully measuring the star's wobble, calculating the speed of its orbit, astronomers could use basic orbital mechanics to determine the mass of the invisible object it was dancing with. The result was astonishing. The invisible partner was 33 times the mass of our sun. It was named Gaia BH3.
A stellar mass black hole, far heavier than our standard models of dying stars predicted should exist in our galaxy.
But here's the crucial part. Because Gaia BH3 is in a wide orbit, far enough away from its companion star, its gravity isn't strong enough to siphon off any stellar material. It isn't stealing any gas.
So no disk.
Therefore, it has no accretion disk, it has no glowing halo, it has no jets, it is completely, utterly dormant, emitting absolutely nothing.
Just imagine that for a moment as you rest in the quiet of your room. Think of these silent sleeping giants. Spheres of pure, localized, extreme gravity drifting quietly through the spiral arms of our Milky Way. They are perfectly cloaked in the velvet black of space, completely invisible to all our telescopes, known only by the gentle, rhythmic, invisible tug they exert on the stars that happen to wander too close.
It is a peaceful, if awe-inspiring thought, to know that the dark holds structures of such immense power, resting quietly.
We've seen how they are born in the violent, sudden collapse of giant stars, We've seen how they warp the fabric of reality and how they feed from glowing disks of plasma. But a profound question remains. Do they live forever?
That's the question.
In the grandest, quietest stretches of deep time, long after the last stars have exhausted their fuel and burned out, will the universe belong entirely to the black holes?
For a long time, physics assumed the answer was yes. Black holes were thought to be eternal vaults. But in the 1970s, a theoretical physicist named Stephen Hawking realized that even these eternal vaults are not immune to the laws of quantum mechanics.
Oh, right.
In the absolute quiet of deep time, they actually very slowly evaporate into the night.
This brings us to a conceptual collision. Hawking did something incredibly difficult. He took the smooth, continuous, curved spacetime of Einstein's general relativity and combined it with the jittery, probabilistic, microscopic world of quantum field theory.
It was a masterstroke of theoretical physics. Quantum field theory tells us that space is never truly empty. Even in a perfect vacuum, completely devoid of atoms or light, the underlying quantum fields are constantly undulating.
Like a bubbling froth.
The uncertainty principle dictates that energy can fluctuate. Because energy and mass are interchangeable, as we learned from E=mc², these energy fluctuations manifest as pairs of virtual particles. A particle and its antimatter partner constantly pop into existence, borrow a tiny bit of energy from the universe, and then, a fraction of a microsecond later, they collide and instantly annihilate each other.
Paying the energy debt back to the vacuum.
Exactly, paying it back.
It is a continuous, invisible, bubbling froth of creation and destruction happening everywhere, all the time, even in the room with you right now. But Hawking asked a brilliant question. What happens if one of these virtual pairs pops into existence exactly on the boundary of a black hole's event horizon?
The geometry of the horizon changes everything. Normally, the pair annihilates, but at the horizon, the gravitational pull is so extreme that the pair can be ripped apart.
Right before they touch.
Right. One particle happens to form just inside the event horizon, or is instantly pulled across it, falling past the veil of no return. But the other particle forms just inches away on the outside. It is violently accelerated by the gravity, but it manages to escape into deep space.
Okay, wait, I need to push back here, because this is where the mechanics always get blurry for me. I understand one particle escapes, but why does that make the black hole lose mass?
Well,
The particle that fell in adds its tiny bit of mass to the black hole, right? So shouldn't the black hole stay the same size or even grow?
that is exactly the friction point where quantum mechanics meets gravity. To understand why the black hole loses mass, we have to look at the energy debt. When the virtual pair pops into existence, they borrow energy from the vacuum.
Right.
Because they didn't annihilate, that debt must be paid. In the mathematics of this interaction, the escaping particle becomes a real particle, flying away with positive energy. To balance the cosmic ledger, the particle that falls into the black hole must carry negative energy relative to the outside universe.
Negative energy.
Yes. In the bizarre mathematics of curved spacetime at the horizon, the infalling particle has negative energy. And because energy and mass are equivalent, negative energy is essentially negative mass.
Wow.
When it falls into the black hole, it literally subtracts a microscopic fraction of the black hole's total mass.
Wow.
The escaping particle, meanwhile, radiates out into space. This faint glow of escaping particles is known as Hawking radiation.
So the black hole is glowing, very faintly, not from an accretion disk of gas, but from its own steady, relentless loss of mass.
Yeah.
It is a slow, agonizingly long process of evaporation. And the rules of thermodynamics apply here in fascinating, counterintuitive ways.
They do. In our normal experience, if something loses energy, it cools down, but black holes have a negative heat capacity. The temperature of the thermal Hawking radiation is inversely proportional to the black hole's mass. The larger and heavier the black hole, the colder it is, and the slower it evaporates.
To give you a sense of scale, a black hole with the mass of our sun is incredibly large compared to a quantum particle. Therefore, its Hawking temperature is just 62 nanokelvins. That is infinitesimally close to absolute zero.
It is so cold that it is far colder than the ambient temperature of deep space. Space is permeated by the cosmic microwave background, the faint, lingering heat left over from the Big Bang, which sits at about 2.7 degrees Kelvin above absolute zero.
So it's actually absorbing heat.
So right now, in our current epoch of the universe, stellar black holes are actually absorbing more background heat from the universe than they are radiating away through Hawking radiation. They are technically growing.
But the universe is expanding. And as it expands, that background heat is stretching out and cooling down. Billions of trillions of years from now, when the stars are dead and the universe is cooled to a fraction of a degree above absolute zero, the balance will tip. The black holes will become hotter than the empty space around them. They will begin to lose the battle.
They will slowly shrink. And this is where the negative heat capacity accelerates the process. As they shrink, they get lighter. As they get lighter, they get hotter. As they get hotter, they evaporate faster and faster.
Speeding up right at the end.
A slow, trillion-year simmer becomes a rapid boil. Until, in their final microscopic moments, the temperature spikes to infinity and the black hole vanishes completely in a brilliant final flash of high-energy thermal radiation, leaving nothing behind but a featureless gas of photons drifting through the endless dark.
So what does this all mean? If a black hole eventually evaporates completely, we run headfirst into one of the greatest, most profound unsolved mysteries in modern physics, the information paradox.
This raises an important question, perhaps the most important question in theoretical physics today. It represents a profound fundamental conflict between the two great pillars of our understanding, quantum mechanics and general relativity.
Let's lay out the rules of the conflict. Quantum mechanics has a strict, unbreakable rule. Information cannot be destroyed. Now, we aren't talking about information like the text in a book or data on a hard drive. We are talking about quantum information, the exact physical state, the spin, the position, the fundamental blueprint of every particle.
The universe is deeply deterministic in this quantum sense. The rule states that the current state of the universe contains all the information needed to calculate its past and its future.
Right.
If you take an encyclopedia and throw it into a roaring fire, the physical book is gone. But quantum mechanics says that if you had a supercomputer powerful enough to track the exact trajectory of every single molecule of smoke, every photon of heat, and every speck of ash, you could, theoretically, run the physics in reverse and reconstruct the exact words on the pages.
So the data is just jumbled up.
The information is scrambled, heavily encrypted by the fire, but it is not lost. It still exists in the universe.
But general relativity, combined with Hawking's original calculations, says something deeply troubling. Let's run the thought experiment again. If you throw that same encyclopedia into a black hole, it crosses the event horizon. It's gone from the observable universe, trapped in the steep jello of space-time.
Eventually, the black hole evaporates into Hawking radiation. But when Hawking did the math in the 1970s, he calculated that this radiation is perfectly thermal. It is completely mathematically random.
Completely random.
It depends only on the total mass, spin, and electrical charge of the black hole. It contains absolutely no blueprint, no subtle signature, no quantum memory of the encyclopedia that fell in.
So if the black hole eventually completely disappears and the radiation left behind is just featureless static, the quantum blueprint of the encyclopedia is gone, truly irrevocably destroyed.
And if information can be destroyed, the fundamental laws of quantum mechanics break down. The mathematical foundation that describes the atoms in your body, the light in your room, and the chemistry of your brain would be flawed.
That's a huge problem.
It was an intellectual war that raged for decades in the physics community, famously between brilliant minds like Leonard Susskind, who fiercely defended the laws of quantum mechanics, and Stephen Hawking, who argued that gravity truly was the ultimate eraser.
Does the universe have a delete button? It's a question that keeps theoretical physicists up at night, even if the thought of it is helping you drift off to sleep right now. Today, the general consensus has shifted. Most physicists believe the information must somehow escape, but the mechanism of how it escapes is wildly, beautifully debated.
It forces us to invent entirely new ways of looking at reality. Some theories suggest the information isn't lost, but is subtly encoded in the quantum correlations of the Hawking radiation itself, scrambled so deeply and over such a long period of time that it just looks like noise to us.
Then there is the holographic principle, championed by Susskind, which suggests that the 3D information of the infalling book is actually smeared and stored as 2D data on the surface of the event horizon itself, like a cosmic hologram, and it imprints onto the outgoing radiation as the black hole shrinks.
Others propose radical, mind-bending ideas born from string theory, like the fuzzball hypothesis. This theory argues that the event horizon isn't an empty, smooth mathematical boundary at all, but a tangible, violently tangled ball of vibrating strings that physically absorbs and then reflects the information back out.
Or replica wormholes.
Right. The more recent mathematical models proposing replica wormholes, where the very geometry of space-time weaves hidden, microscopic tunnels connecting the interior of the black hole directly to the escaping radiation outside. The universe, it seems, fiercely protects its memories.
As we reach the end of our journey tonight, let's gently bring it all back home. Back from the edge of the event horizon, back from the deep time of the cosmos, to the quiet, dark room you are resting in right now.
Mm.
It can feel dizzying, perhaps even a little overwhelming, to think about the extreme curvature of space-time, the crushing weight of singularities, and the slow, cold evaporation of black holes over trillions of years.
But remember this grounding truth. The wild, curved, mind-bending geometry we've been exploring tonight is governed by the exact same physics that hold you safely and warmly in your bed. It is a single, continuous, unified reality.
The atoms drifting lazily in the air of your room, illuminated by whatever faint light creeps through the window, are the very same atoms Einstein studied to prove the granular nature of reality.
They are.
The resting mass of your body, quietly interacting with the gravity of the Earth beneath you, is part of the same continuous fabric that forms the dark, silent event horizons in the deep space of the Milky Way. You are not separate from the cosmos looking in. You are a quiet, resting piece of it.
As your breathing slows and the concepts of light, gravity, and deep time blur together, allow the vastness of the universe to be a comfort rather than a void. The mechanics of reality are functioning exactly as they should, maintaining the architecture of the night.
As you drift off, we want to thank you for listening and for taking this journey with us. Remember to visit the YouTube channel Decoding the Dark. Please like, subscribe, or leave a reaction or so to support our journey through the stars.
Before you completely surrender to sleep, I want to leave you with one last mesmerizing thought to explore in your dreams. We talked heavily about the singularity at the very center of a black hole, a mathematical point of infinite density, a place where all our equations for gravity and quantum mechanics break down and return nonsense.
Right.
But some theoretical physicists suggest that this infinite singularity is an illusion. It doesn't actually exist.
If it doesn't crush down to a point, what happens?
They propose that as matter collapses inward, reaching unimaginable densities, the extreme gravity eventually triggers a profound quantum effect called mass inflation. Instead of crushing down into an infinitely dense point of no return, the collapsing core reaches a limit and then it rebounds.
It bounces back.
The geometry flips. It creates what physicists call a de Sitter core, a microscopic, localized pocket of highly repulsive space.
A pocket of space that violently pushes outward instead of tolling inward.
Yes, but it doesn't push back out into our universe. The geometry is severed. From the inside of that microscopic pocket, the geometry of that outward expansion would look exactly like a rapidly inflating cosmos. It would look exactly like the Big Bang.
Wow.
What if every single black hole in the night sky isn't a bottomless pit, a dead end of space-time, but rather the hidden, silent birthplace of a brand new, expanding universe? Billions of cosmic seeds tucked safely away in the dark, completely cut off from our own, blooming in dimensions we can never reach.
A universe resting safely within a universe, just as you are resting now. Protected, quiet, and full of infinite possibilities, we wish you a peaceful, deep, and restful night.